Hey, welcome back. We're still working polar rectangular conversion, and so far we've just done coordinates of points, easing our way into this, but we're still at the bottom of page 3 of the polar packet, and I just want to mention a couple of things. Something to watch out for. I'm going to add an example here at the bottom of page 3. I'll call it 12b. Just to be careful, and I've got my calculator handy, when there's points where I don't necessarily recognize an exact value, and I want to be very careful of what quadrant I'm in. I want to pick a point, I picked the point -2, -3. And let's say this is just like the directions for 12. You have x and y, you want to get r and theta, so you want to go rectangular to polar. And I got to be more careful because, as I mentioned, what am I, -x, -y, I'm down in Q3. The whole way through, if you have options for a positive or negative radius, either might work. And if you have options for theta to be in different quadrants, the best is going to be if we can make this thing land in quadrant 3. So you have x and y. Again, to get r and theta, we can use Pythagorean theorem. R squared needs to equal x squared, the number 4, plus y squared, the number 9. So r squared is 13. We would be able to use either positive or negative square root of 13, but we're going to have to stick to one in our final answer when we go to choose. Theta comes from the tangent, right? Tangent of theta is going to equal the ratio of the y to the x. Right? So -3 from the original point over -2. I need the arctangent, or the inverse tangent, of 3/2. So we'll say tangent inverse of 3 over 2. Think about it. The calculator is going to give me an answer that's hopefully either in quadrant 1 or quadrant 3. I'm expecting those to be the two spots when you go once around the unit circle that tangent is positive. So I'm in radian mode, and I will inverse tangent in radian mode 3/2, 1.5. And I get rounded in quadrant 1, 0.983. That's your Q1 reference angle. If I put square root of 13 and 0.983, I will not get credit. And do you know why? This lands me in quadrant 1 where I don't want to be. I want to be in quadrant 3. So there is one quick thing you could do to this answer and have it be correct. I could put a negative sign in front of that r, and this would be okay, because you'd be over in quadrant 1 at 0.983, square root of 13 units out, and it would flip-flop you down to where you need to be. This would work. If you're ever in I'll circle this as a potential solution, but if you're in a situation where you need a positive radius, sometimes it just makes things easier to have a positive r value. That's no big deal. We can handle that. Use positive square root of 13, and then think to yourself, oh, I have a reference angle here and here, these vertical angles of 0.983. Here's pi. Let me just add pi to that, and that'll put me in quadrant 3. So a little bit more calculator work. Theta is going to equal roughly 0.983 plus pi. In the calculator, that'll round to 4.124. So this is a quadrant 3 radian measure, rounded of course, 4.124, which also suffices. If I'm ever going to be picky about what your r can be and what your theta can be, I'll state it in the directions, but both of these versions will work pretty well. Lastly, we can convert points, which is kind of cool. We should also be able to convert equations. And if you thought converting points was fun, wait till buckle your seatbelts, boys and girls, because this is going to be even better. We only have time for a few of these, but I figure we just get our feet wet with them. We just try them out. The first one just says, okay, I have this equation. Do you know what that graph would look like? X equals 10. It's the equation of a vertical line, right? A vertical line where all the x coordinates on that line are going to be 10. It says convert to polar form, so I need to get rid of x's and y's in this situation and get r's and thetas. I can use those same 4 facts from the top of the last page. Specifically, x is going to help me here. X equals, we wrote down r cosine of theta. So here we go. Instead of writing x equals 10, can you write r cosine of theta equals 10? Believe it or not, this is polar. This checks out. Now, where manageable, where it's not too much of a pain in the neck, you're going to solve for r, get r by itself. So this equation could look like that in polar form, or if you want to write it in the cool way, 10 secant of theta is equivalent. So that equation in polar form will graph you a vertical line. Keep it in mind. Let's look at the next one. I think 14 is good. We have to find a way. You have x's and y's all over the place in this example, and you want to just have r's and thetas. So what could we do? It's kind of cool with these because there's no one right way to do it, and people always come up with newer, better ways, and it's very interesting to me. I'm looking at the left side. I feel like I have an equation, r squared always equals x squared plus y squared, and I could finagle the left-hand side of this equation to get this expression and call it r squared. Go ahead and do it. Let's pull a 2 out, and you have x squared plus y squared equals 5y, and this conveniently can just be written as r squared. Left-hand side's handled. No more x's and y's, just an r squared. On the other side, we have this y that's problematic. We want to get rid of it. Well, did we have another equation we used for conversions? What was y again in terms of r and theta? Y equals r sine theta. So it's like a little cool polar trigonometric puzzle. Here's the puzzle piece. You got to put it in the right spot. 5r sine of theta. Now, sometimes you do something to make this look more aesthetically pleasing. There's a factor of r that you can cancel from both sides here, and it's not wrong to do that. So if you want to just cancel an r from both sides, that's legal. So this will turn out to be equivalently 2r equals 5 sine of theta. And here it's pretty manageable to solve for r. We could divide by 2 and get r by itself. So r equals the constant 5/2 times the sine of theta will get you what shape? I should have asked you this in the original. In the original, what does that look like to you? It's like all the different maths we've talked about this year are meeting up in this one question. Looks like x squared and y squared with the same coefficient. This is going to be the graph of a circle. So this is a circle, we'll say, right? And so is this in polar form. Okay, can we go the other way around? Let's look at 1 or 2 from this section. 17 says, go the other way around, convert the equation to rectangular form. All you know right now is theta equals negative pi over 4. I gotta think. Those 4 conversion facts on the other side, one of them should be helpful. What was the one with theta and x and y? I believe it was the last one we wrote down, that tangent of theta equals y over x, always. So if we took the tangent of this, right, well, actually, if this is theta, I can plug that in for theta. So I'm going to write tangent of negative pi over 4 equals y over x. I should have written here, where manageable, solve for y, because we usually see rectangular equations in terms of y. Also, test out your exact values. What is the tangent of negative pi over 4? Well, negative pi over 4 is down here in quadrant 4, where tangent is negative. It has the same 2 coordinates, square root of 2 over 2, square root of 2 over 2 over itself. It's going to be negative 1 is the tangent, the exact value. So negative 1 equals y over x, and y equals negative x. Now I pause here. I'm so happy with myself that I was able to get this answer, but again, I wonder if we could have guessed it by looking at a picture. What does this graph look like? In polar form, it's the line where all of the angles, right, with terminal side falling on that line, are going to have a reference angle of pi over 4, right, in the 2 quadrants where tangent is going to be negative. So negative pi over 4 is this entire line going across. This should look exactly like the line y equals negative x. That shouldn't be a huge surprise. One for the road. You know what? Let's pick 19. So 19 says r equals secant of theta. Circle this one. This is a good one to end on. If I think of the 4 conversion facts, this doesn't look like any of them yet because the reciprocal trig functions weren't in any of them. So maybe I can rewrite this so that I have a sine and or a cosine and or a tangent. Let's go with cosine. R equals 1 over cosine of x. See how, cosine of theta. See how that looks for now. Okay, a little sloppy there. Can I multiply the cosine over so this is no longer a fraction? Well, what do you know? R cosine theta has to equal 1. I'm interested in getting this into completely rectangular form, and I know r cosine of theta equals x. We can call this x equals 1. So this equation was pretty much the reverse of the very first one we did on this page 13, and there it will be in rectangular form. Okay, I said we couldn't get to another one, but I don't know, I can't wait. Let's try 18 too. 18, we've seen 1 or 2 like this before. It says r equals 2. Can you get that into x and y form? How could you relate r to x and y? Use the Pythagorean theorem, right? If r equals 2, what does r squared equal? R squared has to equal 2 squared. It has to be 4. We know this in terms of x and y, we could sub in. So x squared plus y squared equals 4. No reason to solve this for y. This is yet another equation of a circle. This one happens to be centered at the origin, and the radius is 2. And it's something I could have guessed from the original, that polar graph would also give me this picture. Okay, I got to stop myself. This is too fun, but we'll get to more of this in the next part, so I will see you then.